Hello, Ezemy one, and welcome back to Rat Run. I'm your usual everyday time-puzzling rat girl, Ezemy Jika, and today I will be solving Rat Run 16, Schrodinger's Rat. Experiment 16, Turquoise, 27th of November, 1974. The Schrodinger cells in today's maze are a first for our experiments, cells containing two digits rather than one, which will force Sphinx to confront choices that are less straightforward and more multifaceted. The aim is to probe whether her decision-making can adapt to this added layer of complexity and uncertainty. This is indeed the first puzzle where normal Sudoku rules do not apply. Schrodinger cells. Fill each row, column, and box with the digits 0 through 9 once each. To make this possible, each row, column, and box contains one Schrodinger cell, which contains two digits. These can be entered as center pencil marks. The value of a Schrodinger cell is equal to the sum of its two digits. So we're cramming 10 digits into the space of 9 cells by having having two of the digits share. I do love cramming too many things into too small a space, so name of the experiment, we know this, rat to cupcake, diagonal and 2 by 2. Black currents, values connected by a black current have a 1 to 2 ratio. One-way doors, the path can only travel in the direction of the arrow, and which also points to the smaller digit. We've seen those before. Test constraint. In this experiment, oh wait, it is values rather than digits. It is worth noting. So this could be like a sum of like a very large sum or something because of the Schrodinger cells, which are going to be rather difficult to work with. Test constraint. In this experiment, dotted box borders divide the correct path into segments that each contain at least two cells. The values of two adjacent cells within the same segment always have the same difference, and the difference is unique for every segment. For example, if a segment has a sequence of values 1, 3, 5, 7, then its same difference is 2, and so no other segment may have the same difference of 2. These are indeed going to be same difference lines, and on top of that, they will be unique same difference lines. So, there's no real generalizations we can make with an overall understanding of these same different lines, but we can analyze some of the specific differences in a bit more detail. Starting, as maybe somewhat thematic, with 0. Cells with a difference of 0 are equal, so like 1 and 1. Now this will be only possible because they always have to be contained within the same box. It will only be possible if one of the digits is a Schrodinger cell, which I will create a box around. So it is normally it wouldn't be possible for there to be a same difference of 0, at least. However, with the Schrodinger cell, I suppose 1 isn't a very good example. So let's say we have 3, and then we have a Schrodinger cell with 1 and 2 inside of it. They would have a difference of 0 because they're equal. Now, let's look at 1. 1 is the most common difference between all the digits because it is simply the difference between consecutive digits, and thus is the only same difference line that could be of length 9. And in fact, it has to only be of length 9 because if we try and combine some of these other digits into a Schrodinger cell with a higher value, that will be creating a repeat of a different cell and will also be removing another value from the possible roster. So it means that one of these cells will be a Schrodinger with 0. And of course, if we add 0 to something, it remains the same. 2 is the difference between all even or all odd digits. And the greatest number of cells which could be in that path is 6. For example, actually no, I think it can only be 5 because we would have to make this an 11, but we can't make 11 with only even digits. I was thinking that, well, actually no. We don't use odd digits, we use even digits because we can use 0. So 0, 2, 4, 6, 8, that's 5. And then, to make 10, we can use, for example, 1 and 9, or 3 and 7. 1 and 9, or 3 and 7. The longest segment with the same difference of 2 is only 6 cells long. Now, if we go down to 3, we are even more constrained because we can start with 0, 3, 6, 9, and then we could have a Schrodinger cell of, let's see, 12 would be 5 and 7. So a segment with the same difference of 3 could be at most 5 cells long. 4 could be 0, 4, and 8, or 1, 5, and 9, and then a Schrodinger cell. So this one could be at most 4 cells, and the same is true for 5. It could be 0, 5, actually no. For digits 5 and greater, the maximum is only 3 cells. For example, 2, 7, and then a Schrodinger cell. And that is inclusive up to 9. Same difference of 9 is possible between, say, 0, 9, and then, actually no. The largest Schrodinger cell is only 17, and that's including a 9. So I don't think a sequence of a difference of 9 or greater is possible. Or a sequence with the same difference of 8 could be 3 cells long. Yes. A sequence with the same difference of 9 can only be 2 cells long. And beyond that, well, there aren't any sequences of fewer than 2 cells, so what's the greatest difference it could have? Well, at that point, it doesn't really matter anyway. Any 2 cells can have a difference, so as long as it's greater than, say, 5, it doesn't really matter what it is. And with that, let me put this over here. Well, it's fine, whatever. And there's also room for notes down here at the bottom of the puzzle. Since we already know all the rules, let's just get started. The first place we can look is in the starting box, and we've already established that the only sequence with 9 cells is the 1 same difference line. So all of these can contain a 0, and the rest of the digits progress sequentially. So this can be 1 or 9, this can be 2 or 8, this is 3 or 7, this is 4 or 6, and this one is a 5. And all of these can potentially contain a 0, which will not modify their value. Now in this box, we have 2 paths. One is 3 long, one is 7. However, our next longest sequence is only 6 cells long, so the path has to go up this way. And from here, it has to go at least 5 cells before it leaves. In fact, it has to go 5 cells, because if it goes this way, that's another 7. So it has to go out through this way. Now it could be 5 or it could be 6, we still don't know. But if we look at this box, there's 5 cells here already, meaning it can't go this way and become 8 cells. It has to go directly out to here and cannot go through back into the same box. So this is our 6-cell path, meaning these have to be the digits 0, 2, 4, 6, and 8, as well as a Schrodinger cell that adds up to 10. 0, 2, 4, 6, 8. And that means there has to be a 5 over here, because there's no pair with 5 that adds up to 10. And that also means this has to only be 5 cells long, and that is our same difference of 3. Which means the two digits on this crop key, one double the other, also have a difference of 3, meaning they are 3 and 6 in some order. Now, as you can see by our little sequence here, the 3 and the 6 are 1 away from the 0 and 2 away from the 9 and 12. So it has to be 6, 3, 0, pulling a 0 out of these cells. And this one has to be the Schrodinger cell. This needs to be a Schrodinger cell. That can be... What would look good on this grid? Red? I'll make those red. I'll just make them green. Well, anyways, that pulls a Schrodinger cell out of these three, meaning the 0 can't go here either, confirming a 5 for this cell. These three can be any sequence between 5 and 9. This Schrodinger cell has to add up to 12. It cannot contain a 5 or a 9. It can be 8, 4. It can't be 6, 6. It can't be 5, 7. I think it has to be 8, 4. Huh. So that pulls a 4 and an 8 out of these two cells. And these 4 digits then are 1, 2, 5, and 7. There can't be a 5 here, meaning there's a 5 on this inequality. The 1 is not the greatest, the 7 is not the least. Actually, wait a second. They have to go... The 0 has to be on one of the ends of this line, and it can't go here. So it has to go 0, 2, 4, 6, 8, and then this is another Schrodinger cell. Pulling possible Schrodinger cells out of every other position. So this adds up to 10, so it is 3, 7, or 1, 9. Right, and these are just odd digits, 1, 2, 5, 7, 9. This one can't be a 1. This one can't be a 9 or a 3 apparently. So we have all used all of the the sequences of length 5 or more, which means we're left to sequences of only length 4, 3, or 2. In this box, it could be 2, it could be 3. In fact, if it enters this box, it has to only be 3, because it can't go around anyway and be like 4 cells long. If it goes through here, it would have to be 3, because we have to take into account diagonal movement as well. Now, where else can we look? This 4. This 4 is actually, this 4, 8 is actually the digits 4 and 8. So that sees this, which solidifies the rest of these cells. This has to be the 6. Whoops. This has to be the 6, meaning it increases in this direction. So this is 1, 2, and this is 7 or 6, meaning one of these three is a Schrodinger cell with a 0 in it. There's a Schrodinger cell on this sequence as well, which is kind of interesting. We can put these down by Sudoku. So these 4 digits actually are 4, 5, 7, and 8. And what same difference can we make out of those? It has to be a difference of at least 4. Does it have to be 4 actually? Because I'm looking at 4 and 8. That's the greatest difference. Actually, I think it has to be, because we can't have a difference of 1 or 2 or 3, and the largest and smallest digits in this box are 4 and 8, which has a difference of 4. So that means the 8 has to go in the middle, and one of these two cells is the Schrodinger cell containing the 5 and 7, which add up to 12. So the sequence goes 4 to 8 to 12. well, in one of these two directions. These three digits are 1, 2, and 6. The 6 has to be the 6 has to be here. For the crop key dot, these three digits are 0, 3, and 9. They could go in any order because there's nothing constraining them. Cool. Okay, that was a good start. Maybe I can look at these rows. There has to be a Schrodinger cell. Well, actually, none of these can be Schrodinger cells. I think I deleted that before. These four digits are 1, 2, 5, and 9. These two need to be the 1 and 2 for the dot, meaning this is 5 and that's 9. What's a digit greater than 5? It's not 3. Ah, if this is 3, 7, then there's nothing left for this box, so this needs to be 1 and 9. Putting a 7 here and a 3 here. These, well, these four digits, because there's a Schrodinger cell here, are 5, 7, 8, and 0. I forgot about 0. And these three digits, which do not contain a Schrodinger cell, are 3, 4, 6, and 9. Not 9? Not 9. 3, 4, 6, and... Oh wait, they are just 3, 4, and 6. Okay. Right, because there's only 3 of them. So these are 3 and 6, which means this also could be 3 or 6, but it could also be a Schrodinger cell masquerading as a 3, 6, or potentially even a 12. This could have a value of 12. We don't know for sure that it doesn't. These ones, however, cannot have a 1 or a 2, and they have no Schrodinger cells, meaning they're vanilla digits. They can be 3, 6, or they could be 4, 8. They can't be 8, 4 in this order, and they can't be 6, 3 in this order. Now, because we've used our four same difference segments, we can't use it again, which means all future segments are of length 3 or 2, which means we can't go through this path. I guess that side doesn't really matter. The easiest way would just be to go like that, but something tells me it's not going to be that easy. In fact, the path has to go through here, because it can't go enter this box from any of the other entrances. And that might tell us how it reaches the cupcake. So, if it goes from here to here, it has to be 3, 9, because 6, 9 only has a difference of 3, which we've already used. So 6, 9, no, 3, 9 has a difference of 6, which means this would have to be a 15, which is possible, because it could be 7, 8. If it visits this cell first, it could be 6 and then 1. No, that doesn't work, does it? Because this cell is necessarily smaller, meaning that this cell would have to be even smaller than that. Unless it's the same. Because technically, if these two digits had the same value, they would still have the same difference from the center cell. Fortunately, that's not possible to make with a sum of any of these digits. You can't make a 6 with a 0 and a 5 and a 7. So that possibility remains, well, impossible for this box. But it's something to keep in mind for the future, perhaps. So this has to be 3, 9, and what? 7, 8. Meaning these are all vanilla cells. This has to be a 6. And that does mean this is just a regular 3. This 1 and 2 are not solid. So this has to be 8, 4. And it cannot connect to this cell. And I don't think it can go this way either. These have to be 1 and 2. Well, I suppose there could be a weird Schrodinger cell thing going on here with one of these two cells. This part of the sequence, if there's an 8 here, the sequence has to go... How is that possible? I think this is where we employ that same double technique. The last cell on the line has to have the value 8 because there's no way for an 8 to go, say, up to 13 and then go up even further. It has to go, and there's no way for it to go down either because all of these values which are lower are already taken. We can't have a difference of anything below 4, so the smallest difference it could have is 5. And 8 minus 5 is 3, and once we go to 3, we can't go any lower, which means we need to go higher again. And that also means that this Kropke dot won't work, because this needs to be an 8. The last digit needs to have a value of 8. And the only thing that could go next to an 8 is a 4, or I suppose potentially a 16. I guess if this is a 9-7, then this could still be... Oh wait, duh, the Schrodinger cell needs to be the 8, the second 8 in that box. Duh, so it's not going to work. It has to be this cell, the second Schrodinger cell. It has to come around like this and go directly into this box and then go directly into that box, which means it has to wind around through here. 2 vanilla cells with probably a very large difference. So this has to be the 4. This is the 5-7 Schrodinger cell. These have to be 1 and 2. And this is going to be a digit a lot larger than 1 or 2. Let's mark down the differences that we have. We haven't used a difference of 0 yet. We could potentially use it here, though. We've used 1. Whoops. We've used 1. We've used 2. You've used... Well, in order, we have 1, 4, 3, 2. We have something here. We have something here. We have something here. We have something here, here, here. And this one is 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This one is 6. That means we have 11 same differences. And the digits 0 through 9 only count for 10, which means that we're going to have a same difference which is more than 10, meaning that it will have to contain a Schrodinger cell. Potentially 2 of them. Well, 2 of those sums. Okay, these 6 digits are 3, 5, 7, 9, and 0. Forgot about the 0 again. 3, 5, 7. We can pull the 0, 9 off of all of these. And to make 8, we can... Wait. I'm missing a digit. 6. I forgot about 6. So we can still pull 3, 5, and 7 off of this. The only way to make 8 remains 3 and 5. So this is a 3, 5. We can pull 3, 5 off of these as well. Whoops. This cannot be a 7 or a 9 because that only has a difference of 1. So this has to be a 0. That's a 6, 9 pair, putting a 7 here. So it goes 8, 0, 8. Interesting. A very Bob. And then in these 3 cells, what is this? I'll put an 8 here. Meaning we cannot use the same difference of 8 again. This one, it cannot be 6, 2, but it could be 6, 1 because we don't have the same difference of 5 yet. It could be, it can't be 9, 1, but it could be 9, 2, because that's the same difference of 7. Let's see, these three cells are 3, 5, and 6. These three cells are 1, 2, 7, and 9. This 1 and 2 means this also has to probably be 1 and 2. But it's a Schrodinger cell, so anything is possible, really. This has to contain a 0. These digits are 1, 2, well, 0, 1, 2, 4, and 8. So, yeah, one of these three cells is going to be a Schrodinger cell. Let's look at these three. These three cells, actually, there's only three values it can be. There are 0, 9, and what's the remaining digit? 4? Yes. Actually, this has to be a 4. And it can't be a 0 to 4, because that's only the same difference of 4. So this has to be a 9, putting a 0 here, which means this segment is the same difference of 5, meaning this cannot be 6, 1. This needs to be 9, 2, giving us our same difference of 7. This is a 6, that's a 3 and a 9. There's a 2 here, which means this has to be a 1 or a 4. Well, I guess technically this could still be a 0, a Schrodinger cell with another 0 in it. These digits, well, let's look at these first, because there's fewer. This is 1, 2, 0, 1, 2, and 8. Huh. These digits are 1, 2, 5, 6, and 7. Right, because there's 4 cells and a Schrodinger value. This has to be a vanilla crop key, and it can't be 3, 6, so it has to be 1, 2, 4, or 8. Can't be 1 or 2 in that order. Well, this cell does contain a 4, so this can't be a 4 either. Which means this cannot be 8. So it's either 1, 2, or 4, 8. Actually, yeah, this 4 sees this 4, and this 8 sees this 8, even though they're not fully filled in. One of them is just next to a 0. This cannot be 3, 6, but it can also be a Schrodinger cell, which leads to some other shenanigans. So this is an odd digit. This is an even digit. And in order for these to have the same difference as these, this also needs to have an odd value. Which means it has to contain a 1. Because all the other even digits won't work. This could potentially be another ABA situation. And I think it will have to be if it contains 1. So this is going to be 4 and 8. Putting a 0 here, a vanilla 0. Putting a vanilla 4 there. These two are vanilla, meaning the last Schrodinger cell has to be up here. The 8 has to go in this cell, but one of these two is going to be the Schrodinger, and it's going to have to be... Actually, yeah. So there's a couple different ways we can solve this. One is that, well, we have a difference of 0 already, meaning this has to be 9. And the other way is that if this is 1, if this is not the Schrodinger cell and it's just a 1, then the 1 to 0 is, well, that difference has already been used. So this has to be a 4, that's a 7. This is a vanilla cell, that's the Schrodinger cell. Putting the last Schrodinger cell here. That's a 5. Alright, and that means we have used the difference of 9 in this box, in this segment. Which means we have used all of the digits between 1 and 9 inclusive, and we still have 2 segments left. What are we gonna do for them? What difference could they possibly have? These 2 cells are 0 and 9. Okay, that one's a 0. Wait a second. I messed something up, didn't I? Yeah. I shouldn't have put an 8 on this crop key. That was looking so good, too. Why did I immediately put an 8 on that? This can still be a 2, because 4 and 2 is also totally valid. And in fact, it has to be a 2, because there's already an 8 in this column. It's just not detecting it. So this is a 2, this is a 4. I think the logic for the 0 still stands. In fact, I think it has to. Because if this is an 8, or a 0, 8 even, if this is the Schrodinger cell, the 7 and the 9 are only 1 away from it. So this has to be a 0 either way. Putting a 4 here, making all of these vanilla cells. And the logic remains exactly the same. The 7 and the 0 cannot go together. And this has to be the last Schrodinger cell. Yes. Putting a 9 once again here. And our last 2 segments have mysterious sums. This can't be a 7 because that's a 7. These are 0, 1, and 5. Well, there's a 0 here, technically, so this is the 0. These 2 digits are still 0 and 9. Putting a 0 and a 9 here. Let's see. These 2 digits, which are actually 4 digits, are 3, 6, 7, and 8. And one of them is going to be a Schrodinger cell. So that's going to be weird. I don't think this can contain a 3. Well, it could if it's a 3, 7. No. 3, 7 is 9. Well, 3, 6 is 9, which is not divisible by 2. 3, 7 is 10, which would be a 5 on the other side. 3, 8 is 11, which won't work either. If it's just a regular 3 and this is a 6, that breaks this, so this cannot be a 3. This has to be a 3. Wait, this is a 4, because that's a 1. These 3 digits are 1, 3, and 5? Yes. I guess by Sudoku, this is the 3. I guess I could have pulled a 3 out of that with just that. This is the 5. So these 2 digits are 6, 7, 8. One of them has to be added to another in order to make a double. And in fact, it has to be 6, 8 on one side and 7 on the other. Because 6 plus 8 equals 14, which is double 7. And that means the 0 has to connect to the 14 in order to make a valid, well, and not repeated, same difference line. So this one, this sum in this box is 14. Well, the same difference. And I guess it doesn't really, at this point, we don't know which cell it touches, so it could be either one. They make the same difference. Ha ha ha. That's a 1, 5. That's a 1, 2. These 2 cells, the greatest vanilla difference that can go between these 2 cells is 1 and 8. And in fact, we've already established that all differences which are possible between vanilla cells have already been used. So this has to be a Schrodinger cell. Whoops. And that's the last of our... Oh, this one ended up looking like a salad. Like, leaves and all, like, with tomatoes in it? Why do these keep ending up looking like food? Maybe I am just hungry. Pulls a 7 out of this, pulls a 6 and 8 out of these cells. 1, 2, 5, and 7. We have a 1, 2 pair here, putting 5 here and 7 there. So these two cells either need to have a large difference or a small difference. The largest value this one can have is 2 plus 6, which is 8. And the smallest value this one can have is 1. And the difference between 8 and 1 is 7, and anything less than that we've already used, which means they need to have a very small difference. In fact, they need to have a difference of 0, being 8 and 8. Whoops. So that is the last digit of this puzzle, so we can fill in the rest of these to disambiguate them. Yippee! Finks performed remarkably and seemed to not even notice the added challenge, although she was occasionally distracted by the Schrodinger cells themselves. She paused for over a minute to inspect the double-digit cupcake, seemingly intrigued by the notion of two digits coming together in one cell to create a single value, before tentatively nibbling the buttercream. Ah, wow. Two-digit numbers. I guess that's not technically what this is, but... Well, I mean, it is a two-digit number. It is a number that has two digits. It's just that the two digits are not what it represents. This is a 15, not a 78. But maybe 15 and 78 aren't quite that different. That was actually the cleanest solve I've had of the in quite a few days. I like this one a lot. I like the difference of 14 down here. That was funny. And I'm glad I went over the details beforehand too. That helped a lot. So next time, experiment number 17, trapdoors. But until then, mo sono chica desho o Ezemy. I'm still not sure about that.